Up next is Tycho Brahe and his student Johannes Kepler. So this kind of an interesting story, both of them. Two stories, of course, overlap because one is the mentor, one is the student. Tycho Brahe, he lived in 1546 to 1601. So we're actually jumping backwards in time because we talked about Galileo and his use of the telescope beginning in 1609. Brahe died before the telescopic era. I should say the whole category here, I didn't put it up here, but the category is planetary motion. So back to the planets, because remember where we left off. We have Ptolemy's model, which is really good, but it's a geocentric model, and I've now hopefully convinced you that Earth is not the center of the universe. But in terms of the heliocentric model, the best we had was Copernicus's model. And his original model was pretty bad. To make it comparable, and actually slightly better than Ptolemy's, he had to add epicycles. He also had to shift the orbits a little bit, so shifting the different centers. He had to use the same tricks that the geocentric model used. Although you got retrograde motion automatically and brightness variations, and Mercury and Venus always close to the sun, those things fall out naturally of Copernicus' model. To make it match the tracks of the planets on the sky, he had to add in the epicycles and shifting the difference, and that's very unappealing. So we don't yet have a quote, perfect heliocentric model. So we got to return to the topic and come up with one. So the story picks up with Tycho Brahe, who is an observer and a geocentrist of sorts. He has his own version of the geocentric model. We'll get to that. And he's the mentor of Kepler. We'll come back to Kepler in just a little bit. Let's talk about Tycho. Tycho was the greatest pre-telescope observer. Pre-scope observer. And that may seem kind of like a silly thing. How can you be an observer without a telescope? But back then, there were observers, and what they did is measured the positions of things. The positions of stars, and most importantly, the positions of planets. Because planets are wandering across the sky. If you have a geocentric model or a heliocentric model that you want to test, you test it against the actual positions of the planets in the sky. So someone has to measure that. And he was the best. He could measure positions without a telescope. He could measure it good to 1 arc minute, which is what fraction of a degree? 1/60th. So again, stars, when we take pictures of them with modern day telescopes, due to atmospheric blurring, they appear to be about an arc second across. That's 1/60th of an arc minute, which is 1/60th of a degree. Tycho can measure things to 1 arc minute. Let me put degree here, 1/60th of a degree. Which is poor compared to modern standards, but it was the best in its day, and by quite a bit. He was really good at it. You're probably looking at that picture saying, what's up with that nose there? We'll get to that in a second. I got some good Tycho stories. But first let me explain how he did his measurements. He had a variety of observatories over his life. Well, he didn't own them. He worked for royalty here and there. But here's the basic idea. So you have this building, and in there you have this fraction of a circle that's gradiated. On there you have degrees, and the degrees are broken into arc minutes. And you can see here, if you look on the wall on the left, near the part of it, there's an opening that you look out. And he's just standing there pointing. His underlings are doing the real work. If you look over here to the right, there's someone looking through a sighting. He's sighting, he's looking at a star or a planet through that window, and he has to slide the thing he's looking through up or down until he gets the star square in the middle of the window. And then you just read off of the semicircle how many degrees up it is, how many arc minutes up it is. And you always do this measurement kind of when it's highest in the sky. This would point north-south. So as things cross the meridian, then you take your measurement. And from there you can measure their position in the sky. So he was real good at it. And this enabled him to make a number of important contributions, not just the positions of the planets, but also some things having to do with parallax that actually contradicted his ideas. But you could say he was a good scientist because he put the results out anyway, despite his geocentric beliefs. We'll get to that in a second. Let's tell a few Tycho stories. Anyway, good stories about Tycho. Yeah, what's up with his nose, right? That's story number one. When he was a young man at school, he got into a duel, lost his nose. And I always thought it'd be some kind of noble story about coming to the aid of some fair maiden or something like that. But no, some other student claimed to be a better mathematician than he was, and he took umbrage at that. So it was a nerd fight. But Tycho lost his nose, and I believe it's a metal nose that he wore around for the rest of his life. I believe it was gold. You know, he was from the aristocratic class. He could afford a gold nose, and so there it is. Oh, the other story's on the other end of his life, and I'll tell half of it and save the other half for just a little bit, and that's his death. Now, if you go to most web pages, most sources, they'll actually tell the incorrect story. There's kind of a common story about how Tycho died. It's not at all true. You know, the common story goes that he was having dinner with the king. There's a bunch of them there. The king invited a bunch of people for dinner, and it's not informal like things are today. Really formal. You can't get up and leave the table if you have to go to the bathroom. And they say he was drinking heavily that day, so he really had to go to the bathroom. But he couldn't dismiss himself to go to the bathroom, so he sat there until his bladder exploded. That's how the story goes. Now, the story originates from his detractors. A lot of people didn't really like Tycho. And after he died, they took great joy in telling this story, and it was kind of written down in history. But they dug him up a couple years ago. Well, they did. They just dug him up. And after you die, I don't know if you've heard this before, but your hair keeps growing, your fingernails keep growing. Yeah, I know. It's only because the skin retracts. It doesn't really keep growing. That's the second person who told me that, so I guess I can't propagate the lie anymore. It'd be cooler if your fingernails kept growing. But yeah, your skin retracts, and you get these long fingernails and long hair. And they took a couple of his fingernails. And it was really gross, right? But they took a couple of his fingernails and analyzed them chemically. And fingernails are kind of like a tree with tree rings. The deeper into the tree you go, the older growth that was. You get an extra layer each year. The same thing with your fingernails. They're like ice cores. You take an ice sample, deeper down you go, you're sampling back in time. And so it's a kind of a chemical history of you over the period of time that your fingernail grew. So the last couple of months of your life, let's say. And right at the time of his death, right kind of in the middle of his fingernail, because the skin retracted back, was a layer with an intense level of mercury. An enormous amount of mercury. Like he had to drink a whole cup of mercury to get that level of mercury in his fingernail. And he's a smart guy. They knew back then you shouldn't be drinking mercury. So he was probably poisoned. Someone probably killed Tycho, mercury poisoning. Now, there is a suspect, but I'll save that for a little bit. Okay, so cliffhanger there. Okay, let's go back to his work as an astronomer. Three major bodies of work, three major discoveries. Well, two are discoveries. One is a major body of work that made use of his precise measurements. And the first one is, so this is all under Tycho, the supernova. I'll just abbreviate supernova SN, in case I come back to it, of 1572, also known as Tycho's supernova. Now, he didn't actually discover the supernova. It was visible during the daytime sky. Everybody could see it. What is a supernova? Anyone know? A star that explodes. Yeah, they tend to be massive stars, greater than about 8 times the mass of our sun. Our sun will never supernova. It will expel its outer layers in something called a planetary nebula, which will look really pretty and still kill us. But the supernova is a much bigger explosion, throwing away most of the star into space and leaving a neutron star behind. Anyway, it's a new point of light in the sky, and if it occurs in our part of the galaxy, it can be bright enough to see during the daytime sky. It happens about once every 100 years in our galaxy. And we're long overdue. In our galaxy proper, we're probably about 300 years since the last one. So, all right, let me get this question. How long does it take for the light to reach us? Depends on how far away it is. If it's only a few thousand light years away, it takes a few thousand years to get to us. The galaxy is 100,000 years across. And, we see these supernovae occur in other galaxies all the time. The Prompt telescopes, that many of you are now very familiar with, they're the leading discoverers of supernovae in the southern hemisphere. I didn't even know this. There's some other group using it, and that's just what they were using it for. And what they do is they scan galaxy after galaxy after galaxy every night, imaging hundreds of galaxies, waiting for thousands of galaxies actually waiting for the supernovae to occur, and they catch them. But if you wait just within our own galaxy, you might have to wait 100, 200 years or so. But we're long overdue. It might occur in our lifetime, which would be really cool, a daytime star. How long does it last? Supernovae take about a month to ramp up, sometimes 2 or 3 weeks. They vary a little bit. So it comes up pretty quickly. The first week or two won't be bright enough to see with the naked eye, let's say, but then all of a sudden you have this daytime star, and it will fade away over the course of a couple months. So to be visible in the naked eye, it might be a period of weeks or months during the day, maybe only a few days to a week. Now, there was one that occurred in 1987, not in our galaxy, but in one of the baby galaxies that orbit us, so kind of close to us, kind of in our galactic system, if not our galaxy proper. And it was the first one of 1987, so it's called 1987A. That one was visible, but not like this would be, because this was in our actual galaxy. Is there another question out there? Yes? Would we feel any heat if it occurred in our galaxy? No. It'd just be another bright source of light. It's still, fortunately, very far away from us. We're safe. We don't have to worry about it. Though, I can add to that a little bit. Once you get above 8 solar masses, you get supernova as your end point of stellar evolution. If you get above 20 or 30 solar masses for the mass of your star, when the star goes, you can form a gamma ray burst, which many of you know that's what I study. It's kind of an extreme type of supernova. The physics are a little different, and it expels most of its material in a pencil beam along an axis. And if that axis is not pointed at us, no problem. But if it is pointed at us, even if it's anywhere, say, on our half of the galaxy, that is a big problem. You can cause a mass extinction here on Earth. And the biologists have looked into this, and we have mass extinctions like all the time, every 26 million years on average. But if you go back, I forget which one it was, about 200 million years ago, long before the dinosaurs, that was 65 million years ago, there's one that the biologists and climatologists and all these people think is actually tied to a gamma ray burst that occurred on our half of the galaxy and pointed at us. So it is possible for things out there in space to have an impact on Earth, not just make it pretty light, but most of the time it's just pretty light. Any other? Okay, so he didn't discover it, but he was the one who made the best observations of it, so historically it was named after him. And back then, it was thought that the universe is this unchanging structure. You know, you have the sphere of fixed stars back in the, still in the geocentric model, sphere, fixed stars painted onto it or attached to it, and it's unchanging. You can't add or take away from it. So anything that's changing in the sky was thought to be atmospheric. And back then they had a pretty grandiose definition. Atmosphere, anything between the Earth and the Moon was considered the atmosphere. We now know that the atmosphere is paper thin compared to the size of the Earth, and it's empty space between us and the Moon. But back then they thought the whole thing, the sky went all the way up to the Moon. And so they figured the supernova had to be really close to Earth. It's between Earth and Moon. And he had the capability to test that hypothesis, doing a parallax measurement. Now, we've already talked about parallax, if I recall. You have to forgive me. I'm subbing in the other class, and I forget. They're a little bit ahead, so I've done everything twice, and I forget what I told you versus them. But yeah, we talked about parallax as a proof of the heliocentric model. So same idea. Suppose in this figure here, let's say that gray object is the supernova. Let's say it's between us and the Moon, nearby. Well, all you have to do is observe it from two sides of Earth. If you observe it from point A, it would appear to be around these stars over here. If you observe from point B, it would appear to be around these stars over here. So it would shift. If you could take a picture, you couldn't then, but you could make a drawing. You'd see it here, and then later on it would shift over to the left, or not later on, but on the other side of the Earth. Now, Tycho didn't have access to a telescope on two sides of the Earth, but what you do is you take a picture, and then you wait 12 hours until you've moved over to the other side of the Earth, and then take another picture. And as long as the object that you're looking at isn't itself moving very fast with time, then you can still do a parallax measurement. Now, you might say the geocentric model, Earth doesn't rotate, but the mathematics works out the same that the Earth is sitting still and the fixed stars are rotating. So you can think about it either way if you want. But anyway, if it's atmospheric between the Earth and the Moon, it should have a very easily measured parallax. In the homework, you have to measure one of the exercises is to calculate the parallax of the Moon. Someone standing on the North Pole, someone standing on the South Pole, both of them looking at the Moon. How much does the Moon appear to shift in the sky? And it's substantial. I won't tell you the answer, but it's more than a moon. It's a certain number of moons. So the parallax at that close proximity is like looking at your finger when it's right in front of your nose and shifting eyes. It's a huge shift, and we would expect a huge shift here, easily measurable to the greatest pre-telescopic observer, and he saw nothing. Found no parallax. Which implied that it's very far away. Very far. Much farther than the Moon or the planets. You can measure parallax of planets. So this had to be farther out than the nearby planets anyway. And hence showing that out in the spheres of the geocentric model, there are things that are changing, which kind of was in defiance of the idea at the time. So important. And he was a geocentrist. And he believed in a variant of the geocentric model. So this doesn't exactly match up with his beliefs, but that's what he found. Second big discovery is kind of the same deal. We don't have to spend so much time on it because it's the same deal. There's a big famous comet. Where is it? Here it is. So this was 1. 2 is the comet 1577, just 5 years later. So again, comets were thought to be atmospheric. This was a big, bright one. It was thought between the Earth and the Moon. He measured the parallax of it, and found no measurable parallax. It, of course, has some parallax, very small parallax, but less than an arc minute. Again, pushing it out beyond the Moon into the spheres of the geocentric model, and hence the universe is a changing place. So these are kind of important. But the key thing, I mentioned those two because parallax is important in this course. We'll do a parallax calculation in a little bit, hopefully today. And you have some of the homework. But the third major thing that he did was look at the planets and measure their positions very accurately for decades on end. He looked at Venus, he looked at Mars, he looked at all the planets and took careful measurements of their positions in the sky. It was the best catalog of planetary positions ever, decades in expanse. And with this, you could actually do tests of the geocentric model, the heliocentric model, different variations. If you have an idea for a different geocentric model that might be better than Ptolemy's, or a different heliocentric model that might be better than Copernicus's modified heliocentric model with the epicycles, that would be a valuable, valuable resource. Which brings us in the story to Kepler. So, Johannes Kepler. He's 1571 to 1630. Remember, Tycho died in 1601, so just a few years before Galileo pointed the telescope upwards. Kepler lived through this era. So Kepler was Tycho's student, but he wasn't an observer like Tycho. Tycho puts a lot of value in actually going out and collecting the data. Kepler was more of a theorist. And he was a Copernican. He believed the sun was at the center, we all went around the sun, and being a theorist, a mathematician, I'll put that there too, he had some ideas of how Copernicus's modified model might be improved. He had been studying it, he had some ideas, he really wanted to get his hands on Tycho's data. He asked Tycho many times, can I take a look at the Mars data? Can I take a look at the Venus data? I have some ideas I want to investigate. But Tycho wasn't interested because, one, he's an observer. He worked decades to collect this data. He's not going to just hand it over to some youngster to see what the youngster can discover from it. And also, he's a geocentrist of sorts. And he knew Tycho was a Copernican and, didn't want to let Kepler work on Copernican theories with his hard-earned data set. So this is Tycho's model. It's kind of a modified model. He had to put the Earth at the center for religious reasons. He believed that. And so there's Earth at the center. He has the moon going around the Earth, and he has the sun going around the Earth. But in his model, he has all the planets going around the sun. So it's kind of a hybrid model, but that's what he liked, and he didn't care to let this young guy working in his staff try to challenge him on it. Well, then he died from mercury poisoning, as we now know. And the very next day, his family went looking for the data, because they knew that was his life's work and something of great value. It was all missing. And it turns out Kepler had it. So it makes you really wonder, and I think the academics suspect Kepler murdered his advisor for his data. The family took Kepler to court. Kepler was ordered to return the data to the family, and he returned all of it but the Mars data. He defied the court order, kept the Mars data, and because of that, we have Kepler's 3 laws.